Hello, ladies and gentlemen. Welcome back. You're once again with the Economancer, and today we'll continue our exploration of An Introduction to Cybernetics by Ashby. In this video, we'll delve into Chapter 3, which focuses on the concept of determinacy and the mathematical tools that'll help us analyze complex systems. If you haven't already, make sure to subscribe to my channel and hit the notification bell to stay updated on the series. So let's get started. So in Chapter 3, Ashby discusses the principle of determinacy, a fundamental concept in the study of cybernetics. Determinacy refers to the predictable behavior of a system where the system's future states can be determined by its current state and a set of governing rules. To analyze deterministic systems, we're going to be looking at some key ideas here. So, a fundamental way of looking at this is for these mathematical tools, we're going to be looking at vectors, canonical representation, differential equations, and phase space. These tools will enable us to describe and model the behavior of complex systems in a precise and systematic way. So if we're looking at these key concepts from this chapter, this isn't all of them, but this is, I think, probably the best ones. So we're going to start with a state. So it's kind of simple to say that a system state is a snapshot of all the relevant given information. Now, an important thing about understanding this snapshot for states, the way he kind of sets up time, and I'll discuss this a little bit more, he only processes things or say things are processed through discrete time and not continuous. Now, the argument for this is probably something that I would rely on, that there is no such thing as continuous time in observation. You can only observe discrete portions of time. And so he makes the example of a weather system. So if you want to predict the weather, you have to know what state the weather is in at that time. Then you have to know what's going to end up happening to the state of the weather in the next step. And so again, we'll represent this more through mathematics and some intuition pumps. So determinism versus non-determinism. So determinism, if we know the initial conditions of that and we know the inputs that are coming in, then we know what the output is going to be. We can predict what that is. Lotteries are non-deterministic. Now, we can reduce the probability of what the outcome is going to be through multiple steps, but that doesn't mean that we're actually going to determine exactly what's going to happen in the system. Social systems and social systems theory is non-deterministic for the most part. Now, there's an argument to be made that as time progresses and contradictions are concluded and stuff like that, we know what the next step will be, right? And this is that whole historical institutionalism. And then we've got other theories such as like path dependence leading to outcomes, but it's still probabilistic at the end of the day because individual choices are probabilistic if you take it that far. So determinacy versus non-determinacy, again, we're looking at what we can predict versus what we can't predict. We're going to start off looking at a machine that has a determined path. If we know what the initial condition is and we add the input, we know what the output is going to be. That will allow us to have this determination. So that is how we predict the system's future state based on its current state and the governing rules. Now, when it comes to these governing rules, there's a lot that gets opened up. There's a lot of good evolutionary economic theory and a lot of good institutional theory that basically lives off governing rules as state determination. So consequences of determinacy, again, if we know the outcome, then it's easier to predict and it's a lot better. All right, so operator and operand. I touched on this the last time, but again, it's really important to understand that when we're saying the operator represents the transformation rules and the operand represents the input or the state that transforms. So again, simple arithmetic operation like we did last time. A is in, and then +3, that's the addition. The operator is the addition function, and the operands are the numbers being added. So identifying the operator and the operand in a system helps us to understand those dynamics and the relationship between inputs, internal processes, and outputs. If you think of it from like a neural network perspective, you know what your inputs are, and then you've got all of those internal processes, those nodes, that hidden layer, and then you have your output. You don't want to just leave it as a black box all the time, but it can be, which is, we'll get to that later down the line. Anyway, So a phase space. This is probably one of the most important things that you can take from this. So if you really want to think about what a phase space is, right, this geometric representation of all possible states of a system in phase space, where we're going to have each point's going to correspond to a unique state of the system, and the system's trajectory represents its evolution over time. Phase space analysis helps us visualize the behavior of complex systems and identify patterns, stable points, and other critical features. Like a critical idea behind this, as you can see, we have our trajectory. We have this example of a phase space in this two-dimensional system where we have X and we have Y, and we know what the outcomes are going to look like. If you have more pieces in this phase space, especially stuff in like differential equations with sinks and stuff like that, where you're actually going deep into what's happening in the system and the dynamics of it, it's very important to have a phase space, because that will tell you, like, all right, why are we not at equilibrium in the market? Well, maybe we are. Maybe we're in this revolving or evolving state of equilibrium in the system, because we're passing by that equilibrium state, going above it and below it. You can think of a sine or a cosine function, where you're just going around it, but you're never actually on the equilibrium, but you're always revolving around it. And that's the way I tend to think of economic equilibrium, and I've made a video about that. And this phase space is very important in understanding that. All right, so systems graphs. Graphs in general, diagraphical representation of mathematics has taken on a new run of the mill and taking over all of these kind of old school ways of representing mathematics. If you look at some of the work in quantitative economics and stuff like that, they're way more about these path dependent structures. So you're getting a lot less regression models, and you're getting a lot more diagrammic models that are being used. And I think that that's for the best. And a lot of it comes down to understanding how this system graph works. We're going to have a room of people. Some are friends. We can represent these people as nodes. And then we're going to have a resulting system that shows the relationships among these people in the room. So as you can see here, we have A is with B and D. And then B is with D, and then D is with C, and C is with A. So what this represents here is this friend group that you have, right? So you have like your key friend, that would be A, right? Because C is the friend with A, and then A is the friend with B, and A is the friend with D. D's really only friends with C. And you can actually just imagine this in your friend group and what it looks like and how it exists. It's actually pretty relevant. One day I'll eventually go into social network analysis and all of that, and how social networks, whether it's the centrality, the degree, the edges, etc., can lead us to understand what's going on in social relationships, like who holds power, like the degree centrality measure, stuff like that. That's the person with the most power in the friend group. Or in this case, it could be a system, whether it would be, an engine or a computer. So canonical representation is probably the most important piece to think about here. And the reason why I say that is because this is kind of a great way to understand mathematics. And I wish I'd have read this earlier in my life about understanding canonical representation in mathematics. I think the best way to do it comes later. I don't know if it comes before or after this, but Kurt Lewin in his work on psychological measurement goes into hological spaces for this canonical representation. But anyway, you can think of a car's motion as a system. So this state is described by variables such as position and velocity. And this is going to be influenced by you pushing the accelerator or pushing the brake. So we're going to make a mathematical model that relates the car's state at one time to its state at the next time, given those inputs. All right, so it looks like a bunch of nonsense. This way of expressing a system's behavior using this standard form that involves state vectors and their transformations, canonical representation simplifies the analysis of complex systems by providing a uniform framework for comparing and studying their behavior. So if we're really trying to lay it down in simple terms, this is a mathematical way to describe a system's change over time. So in this case, as you can see, we have a linear system, which means the relationship between the variables is linear. I know some people may not get it. So let's break it down. So we have x of t. This is a state vector that represents the condition of the system at time t, that's present. It's a list of variables, for example, x1 and x2, that describe the system's current state. Then we have xt plus 1 is the state vector representing the condition of the system at the next time step, t plus 1. And then we have A, that's our transition matrix. This is a collection of values that describe how the state variables relate to each other and how they evolve from one time step to the next. It captures the relationships and dependencies between the state variables. Then we have U of t. This is the input vector at time t, right? So as you can see that, so we have our input vector at time t. It represents any external inputs or influences affecting the system at that time. Then we have B as the input matrix, which represents how these external inputs affect the state variables. So now the equation xt plus 1 is equal to A times xt plus B times ut. Tells us how the system's state changes from time t to t plus 1. So we kind of multiply the current state vector xt by the state transition matrix A. This gives an intermediate state, which represents how the state variables would change based only on the relationship with each other. Then we multiply the input vector, so what we're giving the system, by the input matrix B to find how the external inputs affect the state variables. Finally, we add the two results together, and then we get the state vector of xt plus 1, representing the system state at the next time step. And something to think about here when we're thinking about this, let's think about the operator and the operand. So if we're understanding this deterministic system, and we have this distinction between our operators and our operands in this context of this canonical representation, an operator is a mathematical function or transformation that acts on the system state or input vectors, such as the state transition matrix A and the input matrix B. On the other hand, we have operands, are the objects being acted upon, such as the state vector x of t and the input vector u of t. In this equation, we have A and B are the operators that determine the state vector, and input vector influence the system's future state. The state vector xt and the input vector ut are operands, as they are the objects being acted upon by the operators A and B. When we're trying to understand deterministic systems, we need to understand the roles of operators and operands, because this helps us better analyze the system's behavior and predict future states. This concept is applicable to various mathematical representations of systems, not just the canonical representation. All right, let's move on to the next one. It's a lot. So, unsolvable differential equations. This is hilarious to me because a lot of people don't know, but there's tons of differential equations out there that cannot be analytically solved. So, what do? We have really, really powerful computers use numerical methods and simulations to provide approximate solutions and insights into the system's behavior. There's always a joke between applied mathematicians and theoretical mathematicians, where the applied mathematician will look at the theoretical and go, well, why don't you just do proof by approximation or proof by brute force? And the idea here is that there's no closed form solution for what you're working on, but I can get you something that's 99.99999% of it. And this absolutely causes, a great amount of anger. Let me take a step back. On differential equations, we have to understand that differential equations describe the relationship between the rate of a change of a system state and the state itself. So Ashby uses differential equations to model the dynamics of a deterministic system and predict their future states based on their current conditions. For example, a simple differential equation representing a system's growth could be like dx over dt is equal to kx, right? Where x is the system state, t is the time, and k is some constant, and you'll just see its fluctuation go on. So system closure. So let's talk about a system. Ashby defines a system as an interconnected set of components that interact according to specific rules. A system can be deterministic if its behavior is predictable, or non-deterministic if its behavior is uncertain or subject to random influences. And if you look here, and what we were talking about earlier, or the last video on systems closure, systems are closed if the transformations within it are closed. That means the output depends only on its current state and not on the environment. And this is why I said when you go into like further evolutionary or ecological systems theory and stuff like that, it really starts being about those governing rules and how those play into the dynamics of the system itself. And again, we have this mechanical clock. It's a closed system. Its behavior depends solely on its internal components and their interactions, regardless of external factors, which is something to really think about. Okay, so we have systems transformations. We know that systems transform. It takes input data, processes it according to internal algorithms, and generates an output. Sometimes these internal algorithms, these transformations are black boxes, and that is for the video after the next video. So one of the big discussions that Ashby has in the very end is on science and chaotic systems. He's basically like, all of these scientists keep saying we shouldn't study chaotic systems or things that are nonsensical, and we should only really worry about things that are systems because they're machine-like. And he's like, well, first of all, you're making an epistemological error, because you're only looking at our current set of knowledge and our understanding, and this may over time change. So not studying it now means that we're negatively impacting that future study of it. So we should probably do it now. And then he also makes the statement as in saying that even if there is determinism in all of the systems, there's enough chaos or complexity that we can learn more and more and more about these complex dynamics as they happen. And those complex dynamics of studying something, so communications theory, understanding some of those complexities will allow us to understand complexities in the social system. Why did complexity or understanding like redundancy in communications theory matter? Because it allowed us to understand how our language pattern works between each other, or communications in general. But where did this come from? Well, that came from physics. And this is like a big battle that goes on in academia, where we have people that have like this determinism undergirding all of their mathematical models. And then we have others who say like, oh no, it's so complex, we can't use mathematics. There's a royal road between the two. And that's what Ashby's trying to point at here, is getting people to understand this royal road, this middle line between understanding that some things are too complex and too chaotic to really understand, but there's also good reason to study that complexity and that chaos itself, because that will have spillover effects in other places. So, to conclude, in this chapter, we covered the concept of determinacy, which is fundamental to the study of cybernetics. We also discovered several mathematical tools that help us analyze deterministic systems, such as vectors, canonical representations, differential equations, and phase space. By understanding determinacy and applying these tools, we can predict and control the behavior of complex systems more effectively. And I'm sure some people will be like, whoa, predict and control. There's a reason for wanting to control stuff that's outside of authoritarianism, right? That's a whole nother video. We'll get onto it someday, eventually, maybe. So that wraps up our discussion of Chapter 3, The Determinate Machine, from An Introduction to Cybernetics by W. Ross Ashby. By understanding the concept of determinacy and mastering these mathematical tools introduced in this chapter, we can better predict and control those behaviors of those complex systems, which is the cornerstone of cybernetics, is to understand, predict, and control the behavior of complex systems. So in our next video, we'll explore Chapter 4, which covers the concepts of machine with input. Don't forget to subscribe to my channel, hit the notification bell to stay updated on the series, you have any questions or comments, feel free to leave them in the comment section below. I'll see you in the next video. Hopefully it won't be as long, but I have a feeling that it will be maybe longer. I think as each one of these chapters continue forth, especially when we go to variety later down the line, that's going to be broken up into like 5 episodes, because it's just going to be an important part, especially moving forward and understanding like political theory from Durkheim to sociological theory from Parsons and Luhmann. All of this is going to be built on this understanding of variety by Ashby. Anyway, have a good one.